base graph of sine looks like. Then we're going to do cos. Then we're going to do very funky tan. Then we're going to stretch them, compress them, reflect them, translate them. So you notice first off it looks a little bit different because I have a really long x-axis, really short y-axis. Why is that? So why do I have a really short y-axis? Yeah, we know that it can't be bigger than 1 or minus 1, so I only need 1 unit on each direction up and down. And for the units along the x-axis, I'm just going to use the unit circle points. And I'm going to space them out so I have lots of room. So we know a unit circle starts at 0. Top of the circle is perfect. Left-hand side. Bottom of the circle. And all the way back around. So I've chosen to do it that way instead of 1, 2, 3, 4, 5, for example, because pi we know is 3.14. So it'd be kind of hard to judge where that is. So we're going to do it in the unit circle values. Okay, so let's talk about sine. So you're picturing the y coordinate. When we start the circle, the right-hand side, what is the sine value at 0? So right-hand side of the circle, what's the sine value? What's the sine value? 0. Top of the circle, 1. Back to the left-hand side, 0. Bottom of the circle, and all the way back around. Here is your first trig graph. You notice they're nice curves. They're kind of parabolic. It's not straight lines like connect the dots. I'm trying to load a website, but I think the internet might have just gone down. No, my computer might have frozen. Oh, wait. Ooh. It seemed to have liked that. Yes, I am. Come on, internet. What did we do before the internet? I don't know. I guess you guys don't know life before the internet. That makes me feel really old, a little bit. So I'm just going to play you a quick video. It's 30 seconds. And there's no words to it. What they're going to do is they're going to do a rotation around the unit circle. So you'll see here on the left. And at the same time, they're going to plot the coordinates along the axis. Because the problem is the circle goes like this, but in terms of time, we can't go back in time. So you can't just draw a circle on the axes. So you're going to see a point go around the circle. It'll start at 0. And then you'll see the corresponding graph in time. It's on freeze. You can't see that. What you're going to see in a moment is a point going around the unit circle. It'll start here. And then you're going to see the graph being drawn over time. It is kind of cool, isn't it? It is a wave. That's exactly what it is. There we go. So all we've done really in terms of this graph is go around the unit circle and just plot all the y coordinates. Who are our physics people who did physics last year? So this should not be a surprise because somebody said it's a wave. Of course it's a wave. That's all sinusoidal graphs are. So if you have done harmonic motion, did you guys do that? Which is what we'll talk about tomorrow. Harmonic motion, anything you talk about, waves, sound waves, light waves, it's all this kind of stuff here. We're going to do cos on the same set of axes, so just change colors. I don't care if it's red. I just pick a different color than sine. And we're going to do the exact same thing. So we're going to plot all the cos values going around the circle. So it's 0. So right-hand side of the circle, cos is 1. Top of the circle, 0. Pi. Bottom of the circle. And all the way back around to the right-hand side, 1. Here's the cos graph. What do you notice about these two? So look at them together. They're the same graph, they're just in different spots. If I were to take the cos graph and just push it over one quadrant, so if I were to do a horizontal translation to the right, it would be exactly the cos graph. Sine and cos are actually the exact same graph, they're just one quadrant apart. So in terms of the quadrant, we know between 0 and pi on 2 is quadrant 1. And between pi on 2 and pi is quadrant 2. Between pi and 3 pi on 2, quadrant 3. Thank you, Talbot. And between 3 pi on 2 and 2 pi, quadrant 4. Now let's talk about the cast rule. What do you know about sine in quadrant 1? And that's why it's above the x-axis. What do you know about sine in quadrant 2? Still above the x-axis. What do you know about sine in quadrant 3? And this is why it's below the x-axis, and in quadrant 4, below. Okay, let's look at cos. Quadrant 1 it is, so it's above. Quadrant 2, negative below. Quadrant 3, negative. Quadrant 4, positive. So the cast rule just comes from the graph and whether it's above or below the x-axis. Kind of cool, huh? We call these graphs periodic, and what that means is they repeat themselves over and over and over. So this is just one revolution of the graph, but if I kept going, what's going to happen? Well, it's going to go back down and back up, and if I kept going, back down and back up. So show me way over here on this side, so that for you is left. Put your hand out as far as you can in this direction. And I want you to go up, and then down, and then keep going up, and then down, and then up, and then down. And how long could we keep doing that? Forever. That's called periodic. That's what a graph is. Domain and range. Let's talk about sine first. So match whatever color you use to draw sine. So look to the left, look to the right. We know that it can go beyond into the negative because that's just negative revolutions. So it can go for negative infinity this way, and we know the arrow here means infinity. What's the domain? X as an element of the reals is one choice. What's your second choice? That's a terrible infinity. Okay, what about the range? Look down, look up. So where's the lowest point on the graph? And what's the highest point on the graph? And so we have negative 1 less than equal to y less than equal to 1 if you want to match the XER. Or we have minus 1 to 1. Which makes sense because we know the biggest radius on the unit circle is 1. So we can't go past 1 or negative 1. Match your color for sine. The domain. XER, exactly the same. The range. Why are they exactly the same? Because they're the same graph, it's just pushed over one quadrant. Okay, let's do tan. So same values. Pi on 2, pi, 3 pi on 2, 2 pi, and 0. 5 values of tan, you've already got them memorized. Okay, tan at 0. So right-hand side of the circle, what's the tan value? Sorry? 0. So tan at the right-hand side of the circle, tan is 0. Tan of pi on 2. Okay, how do I draw something that's undefined? How do I draw something that doesn't exist? You can. We did it last year in Unit 8, which is the unit apparently none of you remember. So we talked about NPVs and restrictions in Unit 8, and we drew them. Yeah, and what did we call these? Asymptotes. Asymptotes. Okay, so that's how we graphically represent something that doesn't exist. It's a dotted red line. There's a t-shirt, I don't have it, but it says, "Kiss my asymptote, you mother function." See, I can't wear that to school. I would probably be pushing the limit a little bit. Pi, so left-hand side of the circle, 0. Bottom of the circle, 3 pi on 2, undefined again. Back around to 2 pi. Okay, well that did not give us a lot to work with. So what I'm going to do is I'm just going to put the units in between. So I'm going to mark halfway in between all these units. And what is halfway between 0 and pi on 2? So what's half of the first quadrant? Pi over 4. And what's the same family in quadrant 2? 3 pi over 4. And the same family in quadrant 3? 5 pi over 4. And the same family in quadrant 4? Tan of pi on 4, 1. Okay. Tan of 3 pi on 4. But it's quadrant 2, so it's -1. 5 pi on 4. Ooh, that might be a little bit high. And in quadrant 4, -1. Check out the funky tan graph. So it comes through those points, approaches the asymptote, but never crosses. And then the same thing in the other quadrants. So remember from grade 11, asymptotes you can't ever cross. It just gets as close as possible, but doesn't actually touch. And so let's talk about the cast rule, just like we did with sine and cos. What do you know about tan in quadrant 1? Positive, and that's why it's above the x-axis. Quadrant 2, negative. Quadrant 3, positive. Quadrant 4, negative is all it comes from. Is this a periodic graph? So does it repeat itself to infinity? Sure. So the next one's going to go up, and then the same shape's going to go over and over and over. So grab your calculator. We'll come back to it. So at some point you probably were like curious and hit the tan graph and then got scared and got out. How many of you checked your mode before you started? Shame, shame. That's always the first step with Trig. Why do you need to check your mode? Why do you need to check it? Because we want it to be in rads. And even if you haven't changed it, if you've been playing games on your calculator, sometimes they will change it for you because they're programmed in a different mode. So make sure you always check your mode first, make sure you're in rads. Oh, there's tons of games. Go to the TI website. Okay, I'm going to hit zoom, and what do we pick for a trig graph? Zoom 7. Funky. Sometimes it won't graph the asymptotes, and it really just is hit and miss with the calculator. To program something vertically is very hard because it doesn't exist, and how do you program something that doesn't exist? So sometimes it'll do those nice asymptotes, sometimes it just has the curve and has nothing in between. In fact, when I did it with the other class, there were no asymptotes. It was really just luck of the draw. But you understand that they're there, so if you need to draw it, even if your calculator doesn't, you would still draw the asymptotes. Asymptotes. Domain. This is a funky domain. How do we deal with asymptotes when we have a domain? Well, I'm going to start by saying XER. But then I'm going to say x cannot be equal to. So I'm starting by saying x is everything except pi over 2. So that's like 1 pi over 2. And then 3 pi over 2. If I kept going, what would be the next asymptote? So I was at 1 pi over 2, 3 pi over 2. I'd hit 5 pi over 2, 7 pi over 2, 9, 11. What kind of numbers are those? They're the odd what's? More specific, because we don't use numbers anymore because we have classifications and families. Okay, but could I go backwards? Would I have asymptotes if I did revolutions around the circle backwards? Sure, where would the first one be? Negative 1 pi on 2, and then negative 3 pi on 2. So what kind of numbers are they? The odd integers. That was painful. So k pi over 2. And then just like before, we're going to define k is an element of the odd integers. X cannot be k pi on 2. K is an element of the odd integers. Okay, so mathematically that's saying every single value except 1 pi on 2 and 3 pi on 2 and 7 and 5 and all those odd numbers and the negative ones as well. Okay, the range, look down. What's the lowest point on the graph? Negative infinity because of the arrow. What's the highest point on the graph? Infinity. How do I wrap that all up into one little cute notation? There you go. The exam loves putting this as a multiple choice question. So which of the following represents the domain of tan? And they'll give you a bunch of choices that look like this. Okay, so those are our 3 base graphs. Now we're going to do a whole bunch of things. And I said translations, but this should be stretches and compressions. So, what do stretches and compressions look like? Exactly the same steps we did at the beginning of the unit. So first step is figure out the base graph. So take away the numbers, what's left here? Sine. Now what I do for sine is I just memorize the points. They go 0, 1, 0, minus 1, 0. And those are just the unit circle values. It's where it's coming from. If later you want to draw the cos graph, what's the order of the points? So top is sine, bottom is cos. Again, if you don't want to memorize that, it just comes from going around the unit circle and figuring out what the coordinates are. Okay, so base graph is 0, 1, 0, negative 1, 0. Okay, let's talk about the transformation to out front. Vertical, something, yes. Stretch, I agree. XY goes to. Perfect. So off to the side, let's talk about horizontal stuff with sines and coses, doesn't matter. If you see something like that, sine 2 theta, which we know is a double angle identity, we did that and we put it on our pink card and we did equations and identities and all that kind of stuff with it. What we didn't really talk about is there are imaginary brackets. Whatever follows the sign is in brackets. We just get lazy and we don't put them down. So a 2 in front is a vertical stretch. A 2 tucked in the middle is horizontal compression. Okay, so if it's in between the sine and the theta or the x, that's when you're going to get a horizontal. And when we talked about solving these equations, we said, well, we can't just divide by 2. This one we can, this we can't. Well, because in terms of graphing, these are completely different. This is a horizontal stretch, vertical stretch. That's a horizontal compression. Okay? So what do we do? Well, if you're a point person, you can write down the points. If you're not, we're just going to do it together. Red pen, because it's our last graph. And all I'm going to do is take these values that are right up here, and we just plotted, and I'm going to times them by 2. So 0 times 2. 1 times 2. 0 times 2. Minus 1 times 2. And 0 times 2. And here's our first vertical stretch. But we stop and we ask ourselves, what's the very last question? Did we stretch it? Did we take the top and bottom and yank on this thing and pull it up and down? And it's really easy to see with the trig graphs. Clearly, it's twice as high as it used to be. Okay. No different than what we did with our cubics, our square roots, our parabolas, our absolute value. We're just doing it now with a trig graph. A little sleepy there, Zach? What about reflections? Whew. Kind of exciting here. Base graph, take away the numbers, what's left? Cos. Okay, what do you want to do with cos graph? What's the base graph? How do we draw it? You can't see, but Mariana's actually mouthing it. That's how I'm getting these points. They couldn't hear you. The cos graph, I always think of a roller coaster. I don't know why. So when you're at the top of that hill looking down, and then you go all the way down and then all the way back up. I'm a ride puker, so I don't enjoy that. But I've ever told you my favorite ride at the park? My favorite ride of all time, the bench. It's very exciting. Nobody pukes on the bench. Nobody gets sick on the bench. You get to hold everyone's stuff, go through their purse. The bench is the most exciting ride. I ride the bench. Yes. Yes, I'm a ride puker, so no, I don't. No. I enjoy the mini donuts. Oh, lemonade's the root beer. I like the root beer. Yeah, it depends. Yeah. Yeah, sometimes. Till Mr. Soretta played there, then I stopped going. Did I say that out loud? I think I said that out loud. Okay, left to right. What's the negative? Negative is a vertical reflection, the mapping, perfect. And then what's the 3 going to be? Vertical stretch. XY goes to. And what's the order we do them now? That's way easier. Just left to right. Okay, so no red yet because we're just going to do our reflection first. So whatever color you want. For visual people, sometimes it helps to write this out if you need to see it. If you don't, don't. What's going to happen if I multiply all these by a negative? It's going to go minus 1, 0. Again, if you don't need to write it out, don't write it out. Just a hint for the visual people. So we're going to go minus 1, 0, positive 1, 0, minus 1. That's like the roller coaster when you're at the bottom going up the hill. That's the worst part. I hate that. It's like, chick, chick, chick. Could it be any slower? Look at it before you go on. Did you flip it vertically? Did you do what you said you were going to do? Did you take it and flip it upside down? Okay, red pen. Now, if you're visual and you have these points here already, let's use them. What we're going to do is multiply by 3. So negative 1 is going to go to 0 times 3, 1 times 3, 0 times 3, negative 1 times 3. And if you don't like to do that, you can go straight from the graph. So negative 3, 0, positive 3, 0, negative 3. That's like an even scarier roller coaster. So just 2 vocabulary words that are going to come tomorrow. The height of a trig graph. So from max to the min is called the amplitude. And if you've done physics, you've probably heard that one before. Okay, so height of the graph. The width of one cycle of the graph, or one revolution of the circle, is called the period. And in physics, they got all fancy and called it the frequency. And that is the width of the graph. So beginning to end. One cycle, one revolution. Okay, so we did stretches, compressions, we've done reflections. How about translations? Base graph. Take away the numbers. What do you see? Okay, draw it. Okay, describe the transformations. So go ahead and write down what the 2 and the 4 are. What is the 2? XY goes to? Confirm. What's the plus 4? 4 units. Up. Okay, so if you're the point person, we can come over here and just multiply them by 2. So 1 times 2. 0 times 2. Minus 1 times 2. 0 times 2. 1 times 2. Moving to red because it's our last graph. Again, if you're a point person over here, what you can do is just add 4 to each of these. So what's 2 plus 4? Plus 4, plus 4, plus 4, plus 4. And I think we're going to need some more points. pretend I actually hit that last point there, or the second last point. Stop and look at it. Did you stretch it vertically? You translate it vertically. Write down the domain and range. Now, one advantage to doing these points off to the side is you can easily see the domain and range. Well, the range, I should say. What's the lowest value that you have here in the list? And what's the highest value you have? So you can get the domain right off these points. It's got to be 2 to 6. What about the domain? Infinity to infinity, so either XER or the other one. And then 2 less than equal to y less than equal to 6. And again, that can come from the graph or right from the points. Show me your thumb. How you feeling so far? Good, kind of good. Yeah, you can use the other one, whichever one you like. Base graph. Base graph, yes, coast, draw it. Okay, describe the transformations. Negative pi. Horizontal translation. Pi to the right. -1. Vertical translation. 1 down. What the heck do we do with pi? Well, the units are already in pi. So if we think of this as the first unit and the second unit, how many units are we counting over? 2. So it's either, because they've split this into thirds, so you're either counting 6 if you want to count all the little dashes, or if you think in terms of unit, this is just 2 to the right. That's all it means. Okay, so I'm going to start with my first point at 0, 1. And I'm going to go 1, 2, and 1 down. I'll show you that again if you weren't looking up. 1, 2, 1 down. Okay, the next one at pi on 2 is going to go 1, 2, 1 down. Third one, 1, 2, 1 down. Well, I can't just leave this open graph here because I know that these are periodic and they go on forever. So I can't just leave this. What I would have had to do was think, well, what's over here? So what's on the negative side? Well, I know it would have gone down and then back up. So we're just going to use the periodic nature of the graph. What would have been on this side? So if it was down, going backwards, up, up. Well, it can't go higher than this because this would have been the high point. So it's going to go down and down. There it is. Why are you making that face? Domain and range. There's the offer. Confirm or disagree or change or Thumbs up. We have 3 more to go, but that's going to get into the inverses. So I suggest we pause there, do a little bit, a few questions on this, and then come back, period 5. But it's up to you. We can keep going if you want to. Nope. Okay, so let's pause. Look at page 521. You may not be able to pick the hardest question because we might not have gotten to it yet, but work through a couple of them, see how it goes.